Hello wonderful person, this is Anton, and it's about time we've discussed black holes, and specifically binary black holes, once again. And that's because in modern astrophysics there is really no language more profound than the one spoken by gravity itself. And so for nearly a decade now, since 2015, instruments like LIGO and Virgo have been listening and detecting a lot of gravitational waves, or these very subtle ripples in the space-time fabric, very often created by some of the most violent collisions in the entire universe. Collisions so dramatic and so intense that the vibrations produced by them reverberate for billions of light years. And today we're pretty certain all of this was caused by black holes that eventually combine into one. With the initial discovery of gravitational waves in 2015, confirming the existence of these compact object binaries, fundamentally reshaping our view of these cosmic events. But recent discoveries, fueled by increasingly sensitive detectors, have now moved way beyond confirming the theory. Because now they're revealing some unexpected secrets and strange properties of these black holes, potentially telling us a little bit more about how some of these objects formed, how they behave, and how they interact. And so in this video we're going to be exploring some of these most recent discoveries and discuss some of the more surprising detections from the last few months, but mostly focusing on various facts that seem to challenge current models and seem to teach us a little bit more about the stellar life and stellar evolution. But in general, in cosmology and in astrophysics, observing black hole collisions has now become super important. And that's because they now have two primary roles in science. First of all, these are cosmic laboratories for a lot of fundamental physics. They essentially tell us more about gravitational theories and Einsteinian principles, and help us compare the observations with various predictions. But at the same time, they also tell us a little bit more about galactic evolution, especially when it comes to black holes that are supermassive. Now, this by itself has not been physically detected yet, but we have quite a few candidates we've discussed previously in some of the videos in the description, and at least one candidate we're going to be discussing today. But in general, when black holes orbit one another, they shed some of the energy as gravitational waves, which then slowly causes both of them to spiral closer and closer toward each other. And so in essence it kind of looks like this. And as I mentioned, these gravitational waves travel for a very long time, and though initially very strong, eventually become barely detectable, only visible to some of the most sensitive devices. And so by analyzing patterns of interaction and collision, scientists can usually reconstruct many physical features of these colliding objects, including their masses, the overall distance to this event, and crucially, the speed of these black holes and even their spin. With every new detection, of which quite a few have been discovered recently, helping us understand these objects a little bit more, and most importantly help us understand where these events usually happen, and why we actually seem to be seeing so many more than initially predicted. As a matter of fact, right now scientists are not entirely certain if most of the events we've seen so far happen inside star clusters, with a very large concentration of objects where collisions seem to happen naturally, or if this is more of an event near some kind of a central black hole, where a lot of objects spin around and sometimes collide as well. But let's actually start with the first discovery, coming from this study you can find in the description. And that's because this is one of the first major unexpected discoveries that's now challenging a lot of formation theories and what we previously believed about most of these events. This is known as GW231123 because it was originally detected back in November 2023. And this event seems to be extraordinary because it was the most massive binary black hole merger that we've ever seen coming from anywhere. The black holes in this collision had extreme masses, and they also had extremely fast spin. Basically, they were spinning way faster than they should be spinning. Specifically though, the masses of the component black holes fell inside what's known as the pair instability supernova mass. Or basically they were just too massive to be real. To put this simply, when a lot of massive stars reach the end of their lives, we normally expect them to do one of maybe two things. Either collapse directly into a black hole, or go supernova and possibly produce a black hole as well. But if a star falls within a very specific mass range of about 70 to 140 solar masses, they're supposed to produce a very special event, a pair instability supernova. The explosion that becomes so violent that it completely destroys everything, leaving absolutely nothing behind. No black hole, no neutron star, just a lot of gas. And so we don't expect black holes to form from stars of certain masses. And that also means that we don't expect certain black holes of certain masses to even exist. But in this case, the existence of two black holes with this mass was a genuine puzzle. And for the past couple years, researchers have been trying to answer how this is possible, with this new research possibly uncovering a new missing piece of the puzzle, the magnetic fields. And that's because previously astronomers have actually generally ignored the magnetic field interaction when it comes to black holes, with previous simulations neglecting magnetic fields in most of their models. But in this simulation, a massive rapidly spinning star approximately 250 solar masses seems to actually collapse into a black hole with the exact mass observed in this collision. In this case, it's surrounded by leftover material that seems to be laced with magnetic fields. And if the initial star was spinning quickly, the leftover material forms a spinning disk, causing this newborn black hole to spin faster and faster. And so if this model is correct, it means that it's the magnetic fields that potentially created these types of black holes by basically exerting pressure on the surrounding disk, and thus we should be seeing even more of these black holes in some of the future collisions. But the critical finding here is that these magnetic fields exert pressure on the surrounding disk, with this pressure being strong enough to eject material away from the black hole at nearly the speed of light. And this magnetic outflow ultimately reduces the final mass of the black hole, allowing it to eventually become massive enough to be in this mass gap, or basically allowing it to become this impossible black hole. And so the simulation in this case suggests a profound connection. Strong magnetic fields can slow down a black hole and even carry away stellar mass, resulting in lighter and more slowly spinning black holes that we thought should not be possible. And in contrast, weaker magnetic fields may allow for heavier and faster spinning black holes, which potentially is what's happening in this case. And this particular explanation actually explains the unique mass and spins of these black holes very well. But obviously this is just a model and just a theoretical proposition, so we do need to find more of these black holes to confirm if this is true. Either way, if this is correct, it would deepen our understanding of black hole physics and suggest that we do have to consider magnetic fields in some of the future models just for all of this to make sense. Then, a little bit more recently, we had another discovery from two separate collisions whose names you see right here. This was actually detected not so long ago during the October and November run in 2024. And in this case, this was two binary black hole mergers, roughly around 1 month apart. And here, the properties of these two black hole pairs are statistically extreme. They essentially sit at opposite ends of black hole population. And so the first collision, the one you see on the left, involved two black holes roughly around 20 and 6 solar masses, with the larger black hole discovered to be one of the fastest rotating black holes ever observed. It seems to have the largest limit obtained so far on the spin magnitude of any emerging black hole. And so here, if the fastest spin of a black hole is 1, this black hole was spinning at approximately 0.7, essentially 70% of the final limit. In contrast, the other collision, the one that happened a month later, contained a primary black hole whose spin was actually in the opposite direction to the orbital motion. So basically it had what's known as the retrograde spin, and that's even stranger, which makes this particular collision even more difficult to explain, because in terms of orbital physics, when you have two objects orbiting each other, they're actually supposed to spin in the same direction as well, assuming that they actually formed at the same time in the same location. And so here, because one of the black holes was spinning in the opposite direction, something was not really adding up. And so for both of these collisions, it's really the spin that seems to be a new mystery. In the first case, it's the very rapid aligned spin, and in the second case, it's the anti-aligned spin. And that's on top of the fact that both of these mergers also had a highly unequal mass ratio. There was a much larger black hole colliding with a much smaller black hole. And so none of this was explainable with traditional models, or with formation theories involving black holes that evolve either together or in isolation. And instead, this seems to characterize what we actually refer to as hierarchical merger theory. The theory that suggests black holes are very often formed in dense stellar environments, and environments where black hole collisions seem to be extremely common. And so when two black holes merge, the remnant second-generation black holes, that are typically rapidly rotating and have very specific spins, can then capture a new partner that's sometimes smaller, leading to the second merger. But in some of the previous theories, this was assumed to take tens if not hundreds of billions of years to finalize. So essentially previous propositions suggested that we shouldn't actually be seeing these second-generation collisions yet. But in this case, because we've now seen two such collisions, this implies that these dynamic encounters, involving largely misaligned or even backward spins, seem to be way more common than we thought. And that of course suggests that we just don't understand where these collisions seem to usually happen and why they seem to be so frequent. But in this case, GW241011 also provides us a little bit more clarity and also a really important opportunity to test some of the fundamental laws of physics with unprecedented accuracy. And so, for example, in this study, scientists were also able to test the predictions from the 1963 theoretical proposition by Kerr, one of the first physicists to propose a lot of different solutions to rotating black holes, and who actually predicted many black holes before they were even discovered. And so here this prediction mathematically describes space-time around a spinning black hole, with the black hole's rapid rotation slightly deforming space-time around it, that's supposed to leave a unique signature in the gravitational waves. And so the analysis of this black hole collision surprisingly showed excellent agreement with his predictions and the exact shape predicted by Kerr's solution, which of course was a major win for astrophysics. And this also confirmed some of the major predictions of the general relativity, and once again proved Einstein correct. As a matter of fact, the precision here was so high that it even ruled out a lot of alternative propositions and alternative theories when it comes to black holes. Specifically black hole mimics such as certain boson stars or even quark stars that may resemble black holes. So here this was basically confirmed to be a black hole for sure. Once again, because of that 1963 prediction that was purely mathematical. On top of this, the spin of this black hole allowed scientists to explore particle physics, specifically by searching for hypothetical particles called ultralight bosons. And if these ultralight bosons exist, they are predicted to steal rotational energy from black holes through the process referred to as superradiance. But because this black hole is still spinning super fast, millions if not billions of years after its formation, researchers can now rule out the existence of many of these bosons with certain masses. And so in other words, this particular detection and the analysis of this collision more or less ruled out a lot of alternative propositions and ideas, while also scoring a major win for modern astrophysics. But because these two collisions were so strange, I'm sure we're going to be hearing more about them really soon. And well, last but not least, we also have to talk about some of the more recent discoveries in regards to larger black holes. Here we're talking about supermassive black holes that we expect to collide when galaxies collide as well. But just to be clear, direct detection of these collisions as of today is completely impossible. Mostly because they take much longer time and because they currently produce wavelengths we cannot observe. But in theory, we do expect them to produce something at some point. And so we actually expect a lot of low-frequency gravitational waves with very high amplitudes all over the universe. Now you might want to check out one of the previous videos on the bizarre discovery of this gravitational hum that seems to be all over the place. And well, right now this is the best evidence we have for these black holes producing gravitational waves. But it was actually the discovery from the most famous binary black hole, OJ287, that now provides us with some of the most compelling evidence that there is going to be a collision here at some point in the future. We've actually recently discussed this quasar and some of the most recent discoveries from it in the video in the description, but here we know there are two black holes with a 12-year periodicity that causes very bright flashes every few years. And the black holes here are absolutely ridiculous. The main one is approximately 18 billion solar masses, and the smaller one is possibly 150 million. But the most significant recent discovery was basically this. The first direct radio image confirming powerful jets coming from the primary and secondary black holes, or essentially confirming that both of these black holes are active, and both of them are very close to one another. But the secondary black hole that's a little bit smaller is actually moving so fast that its jet is visibly twisted because of various effects, including Einsteinian effects from the larger partner. And so at this point, this system seems to be the best candidate for a future black hole collision involving supermassive giants. But it's unlikely to happen in our lifetimes. These two black holes are going to be in orbit for a very long time. Either way, in just the last few months, we've had quite a few incredible discoveries about this somewhat bizarre phenomenon that we didn't even know was possible until 2015. As a matter of fact, Einstein famously stated that we'll never actually be able to detect any of this, just because these waves are ridiculously weak and barely even nudge an atom when they pass through us. Yet, here we are. We've detected hundreds of them now, and can even now sense some of the larger gravitational waves coming from some mysterious source whose origin cannot be explained at the moment. Once again, the video in the description discusses this more. And so these discoveries are not just astronomical curiosities. Right now they also serve as very important tests for fundamental physics and can even rule out certain theoretical particles and alternative explanations, essentially telling us a little bit more about the universe we live in. And as future observatories become operational and as LIGO, Virgo, and Kagra go through additional upgrades, we're going to be discovering even more of these events, pushing boundaries of what we know about the universe and the fundamental nature of gravity itself. Which means that we'll come back and discuss this more in some of the future videos once there are some additional discoveries. Until then, thank you for watching, subscribe, come back tomorrow to learn something else. Support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support the channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.